Okay, so now let's take a look here at an example. So suppose that Harley-Davidson's owners make up 14% of all motorcycles registered in the US, and notice that it says all, which means that would be our population. You plan to interview a simple random sample of 500 motorcycle owners. Okay, so let us go ahead here and draw/describe the sampling distribution of the sample proportion of those who own a Harley. And again, since we're looking at the big picture here, I don't know if we're taking every single possible sample of size 500 of this particular characteristic. But because we have the random condition and these other conditions met, we get a pretty good approximation of what the sampling distribution might appear to be. So our first condition that we're going to check is the stated random condition. And so here it looks as though we are told that we have a simple random sample. We have an SRS, which means that our random condition is met. So the first condition is random, and we have an SRS. And so since we're random, we're going to have an unbiased estimator, which means the center of our distribution of this mean of p hat is going to be approximately p, which here we believe is 14%. So the center of this distribution will occur at 0.14. So that's our random condition. Okay, the next one is the independent condition. So we assume that the owners have no influence on the next person, but we're also going to assume here that our random sample of 500, so now we want independence, and this is the 10% condition. We're going to assume that 500 owners is less than or equal to 10% of all Harley-Davidson owners, motorcycle owners, because there's a difference in vehicles here. So that's our independent condition. And because these are independent, I now know that the spread of this distribution, the sigma of p hat, is actually going to equal the square root of p times 1 minus p all over n. So here, our spread of this distribution will look something like 0.14 times 0.86, all divided by 500, and we're going to take the square root of that to give us approximately, it appears, let's see, 0.0155. So now I have my center, I have my spread. The last thing we need is the shape, and again, we're kind of cheating here, but we still need to check the condition. And I'm actually, why is my font so large? Okay. Oh, now I can't see it even better. Okay, so let's go ahead and check the normal condition now, or the nearly normal, or success failure, or large counts condition. But essentially this helps us to do the shape. Where did my cursor go? Do you all see any blue on the, oh, there it is. Okay, I do not like how tiny this one is, but let's see if the normal model is appropriate. We need to check n times p. So here, that would be 500 times 0.14, which that would give us a size of 70. And then we're also going to check n times the complement of p, so 500 times 0.86. And that's going to give us 430. Lo and behold, both of these observations are greater than or equal to 10. So because this condition is met, the normal model is appropriate. And why is it appropriate? Well, it's appropriate by large counts. So that means here, p hat is going to be distributed approximately normal by large counts with a center of 0.14. Because we're using a random sample, we have an unbiased estimator, which means our center is close to that population parameter, and then we'll have the standard deviation of, oh, I got to move my face out of the screen here, and then I lost my cursor. Oh, okay, does anyone see any blue popping up again? Oh, there it is. Okay, so not pan, but p hat is distributed normally at the center of 0.14, and then a spread of 0.0155. And I already feel my students judging me, so I'm going to just fix that really quickly. Yeah, virtual teaching is hard. So this is going to be the sampling, or close to the sampling distribution of our p hat here. Distributed normally by large counts, an unbiased center at 0.14, and then a spread of 0.0155. So I'm going to move my head back over here, and then why does this keep happening to me? Y'all, I promise by like the 28th video, I'll get this down. Okay, here we go. So let's actually use the sampling distribution now to find a few probabilities. Why? Okay. I'm realizing now that the screen acts all funny when I'm sharing and recording and doing all this shenanigans. So you know what? Even better. I'm excited. Okay, so how likely is it that our sample will contain between 13 and 15% of all motorists? Well, let us go ahead here. I'm actually against my better judgment. Here's 0.14. Then we would go 3 standard deviations out, 3 standard deviations below, and we would add this 0.0155. So this would be essentially 0.1555, this would be 0.171, and this would be 0.1865. Down here we'd have 0.1245, 0.109, and then 0.0935. And again, I'm just taking that standard deviation, adding it, and subtracting it. So if I want it's between 13 and 15%, well, 13 is going to happen between 0 and -1 standard deviations, or just between 0 and then 1 standard deviation below the mean. And then 15% is going to occur just right underneath 1 standard deviation above the mean. So if I want my sample to be between, I'm essentially looking for the area of the normal model that is here between 0.13 and 0.15. And we remember that our probability rules, we always start with the parameters. So again, p hat is distributed approximately normally with the center of 0.14 and a spread of 0.0155. So there's our parameters. We have the shape, the center, and the spread. So parameter, next up is picture, which we just drew this here, and then normally I have my students write in the standardized z-scores, and then the observations can go beneath, or since we are already doing the standardized z-scores, I put the observations up here. So we have our, why am I tilting? Okay, we have our parameters, we have our picture. Next up is our probability work, which includes the z-score. So I essentially want the probability that my sample proportion is between 0.13 and 0.15. Now, because 0.13 and 0.15 happen within this normal model, these observations are going to have z-scores that correspond to the respective observations. So what we're going to do now is that we need to find these z-scores. So here, we'll change this up a little. So the z-score for 0.13 we know is the observation minus the mean over the spread. And then we'll need the z-score for 0.15, which is going to be above the mean, so we should expect a positive z-score. And that's true here, right? Because the z-score looks like it'll be less than 1, and the z-score looks like it'll be less than -1 here between these two. Okay, so we are not less than -1. Negatives are weird. It should not be more than -1. How about that? So I'm going to take my probability statement, and the z-score for 0.13 appears to be -0.65. Like we said, it should be under -1. And then, oh, actually I'm not doing p hat anymore because I'm not asking for the sample proportion to be -0.65. I'm asking that the z-score be greater than -0.65, and then that the z-score is less than +0.65. So we would just go to table A here to find this value, or you can just type it into the calculator. I prefer table A, less work to it, but let's see if I have the calculator here. So I am going to select, if you're on your Inspire, you'll go to Menu, Statistics, Distributions, Normal CDF, and in your normal CDF, you do lower, upper, mean, and spread. But because we've already standardized our observations, we're going to use 0 for mu and 1 for sigma. When we get to the AP exam, I will teach you all the shortcuts for the calculator, but until then, sorry, we're cranking them out. So negative, why are you not typing? Okay. negative 0.65 up to positive 6.5 with a mean of 0 and a spread of 1 would give us the probability of about 0.4843. So the probability here that an observation, or that our sample proportion, is between 0.13 and 0.15 is going to be approximately 0.4843. So that's a very likely probability, right? And that's true because we know that within one standard deviation from the mean, you have about 68% of the data. And it's happening in between one above and one below. So that value should be beneath that 68%. 48% is most definitely less than 68. Okay, and then our last question here. What sample size would keep us from being able to use a normal model? So thinking back to the normality condition of large counts, the success and failures must both be greater than or equal to 10, which means the normal model is not appropriate if an observation does not meet that criteria, meaning that NP is less than 10. If it's less than 10, it's definitely not greater than or equal to 10. Well, we know that the P here, and then I'm also going to use some associative property, or just commutative. What's one where you flip it around? Anyways, I know I'm going to have 0.14 for our proportion times our sample size less than 10. And then we just solve this like a regular old Algebra 1 inequality. So that's telling me that a sample size that would be less than 71.42 owners. Well, I, in the context of this question, cannot have 0.42 of an owner, and has to be less than this. So a sample size of 71 would prevent us, and then you would just rephrase the question. And I'll let you guys have all the fun with writing that out. But as we can see here, these are some examples of what a sampling distribution question might look like. Here's how each of the conditions influences the shape, center, and spread of our sampling distribution. Here are some probability calculations. So here's a between. You can have a less than, you can have a greater than, or you could have a percentile question. And then also be prepared to defend the conditions, meaning provide evidence as to why we need the conditions. And we did that on the first video, or on the first set of notes. And also being able to explain variations to those conditions. For example, if the large count condition isn't met, or what would prevent us from having the large count condition met. Or what if our sample size is too large? Or what if we're using a biased sampling method, such as a convenient sample or voluntary response, or a biased question? So those are just a few examples of what the sampling distribution questions might look like. So good luck.